A very good morning to all of you. So today we are going to start our experiment number 5, and experiment number 5 is all about simulating a three-phase sinusoidal pulse width modulation inverter using PSIM software. Now this inverter is going to convert the DC into a three-phase AC output, and the applications are in the variable speed drives, renewable energy systems, and UPS, that is uninterruptible power supplies. So basically, we are having three legs, and each leg will be having two switches, that is the upper switch and the lower switch. And the gating pulses are very different in this case. This is not like your square wave inverter. Now to generate the gating pulses, you need to compare the two waveforms. The first one is a sinusoidal waveform, and the second one is the triangular waveform, or you can say it is a carrier waveform. Now, as you can see that the sinusoidal waveform will be having an amplitude of 1 per unit. It means that the peak value is of 1 plus 1 and the negative peak is of minus 1. Now, similarly, you will be having the carrier waveform, and carrier waveform, the frequency will keep the frequency of the carrier waveform fixed, and the amplitude is also fixed. It means that by varying the amplitude of a sine signal, you can vary the amplitude of the output voltage. So, what is the summary now? That to generate the gating pulses of SPWM inverter, you have to take two waveforms, that is a sine waveform and a triangular carrier waveform. The frequency and the amplitude of the carrier waveform is kept fixed, and the sine waveform amplitude can be varied from 0 to 1. The frequency is fixed for a sine waveform, that is 50 Hertz. So after comparison, the pulses will be given to the switches, and depending upon the switching signals, the output voltage will be appeared across the phase to neutral. In this case, we'll be taking the star connected load, and as you can see that the star connection will be having a neutral. So we will try to obtain the waveform like this. We'll be focusing on the bipolar switching. There are two types of switching, unipolar and bipolar. It means that for that if you take only a one phase will be, that is the S1, S4, that is S1 and S4, or you can say T1 and T4. This is going to operate. This will be operated in a complementary fashion. So for some duration, the upper switches will be on, and for the other duration, lower switches will be on. That is called unipolar switching. But we are more interested in the bipolar switching. So we'll be simulating the three-phase SPWM inverter using PSIM. And after doing the piece that SPWM inverter, the output voltage of the SPWM inverter, if you find the THD, that will be very, very less as compared to the THD of a square wave inverter, because what you are doing, you are shifting the lower order harmonics at a very higher frequency. So how you are shifting? Just by you can see the by setting the frequency of the carrier waveform. The frequency modulation and the amplitude modulation are the two factors which are very important in the SPWM inverter. Now, when you talk about the amplitude modulation, that will be AR upon AC. Now, AR means the reference waveform amplitude, and AC means the carrier waveform amplitude. AC is kept fixed. Now, suppose if you keep AR as 0.8, so the amplitude modulation will be coming around 0.8. Now, amplitude modulation, you will have the frequency modulation, that will be FR upon that FC upon FR. So in this way, you can shift your lower order harmonics to a very high frequency, because the lower order harmonics are are having the higher amplitude, and that can distort the waveform significantly. Okay, so now we will be shifting our attention towards the PSIM software. So, okay, so so this is an inverter. So we will be requiring a DC voltage. So we have connected now. These switches, we can use a MOSFET switches also. Yeah, we'll be using the entire window. Let us see. Okay, so the upper switches have been dragged. So now it's turn off the lower switches. Okay, so okay, can we make the connection? Okay, by using a wire tool, you will have to make the connection. Okay, just a minute. I think this is not proper. I will have to remove this thing. Uh, just a minute. The entire block is getting selected. Right. So this is okay. Again, some problem has been there. It is strongly connected now. Okay. So this is a three-phase inverter because three legs have been used, and in the three legs we will be having six switches that will help in producing the three-phase output voltage. The connection should be very proper. I think you will have to pay more attention to the connection because if you don't connect properly, then you won't be able to get the waveform and the error message will pop up. Okay, so I think the connection has been made. Now we will connect star connected balance load. For balance load, okay, just a minute. I will now this is the balanced. Okay, the resistance is fixed, but normally we will connect RL load. Okay, first we'll try again. I don't know whether it is possible, but let it be. We will keep it resistive load only, and later we will try to change that R load into the RL load. So right, we'll make the connection now. So the star connection, it will have one common point. So the common point has been made. Okay, this is the common point and that is called the neutral. You can connect this common point to ground also. That will be a solidly grounded. So now, okay, so this is the thing. The connection should be there, right? The first is, yeah, the load, this first phase load is connected to the phase number A, or you can say it is the phase number R. Now, similarly, this is the second phase, the third phase. Okay, so now coming to our control circuit, the control circuit is very much important. Okay, so for that you need to compare a triangular waveform and a sine waveform. So the triangle waveform is common sine waveform because as you can see that they are phase shifted. They are phase shifted. Huh? Okay, so we need three comparison block because we are having three phases. So comparison block right here. Okay, I will connect here only for simplicity. Okay, I will just place this. Um, okay, that is right. This is for this comparison. I will have to provide the phase shift accordingly because there are three legs and three legs will operate at different instances. Okay, now what about the triangular waveform? Yeah, the triangular waveform has been taken. So first we'll make the connection. This triangle is common to all. This triangle is common to all. Um, I need to again write. Hmm, so for having the healthy connection, okay. Uh, then this is okay. This one is also okay. This is right. Right, very good. The one thing is, hmm, the connection has been made. Now these are for the control. This is the control part which we are designing now. Okay, so this is okay. Now the frequency has to be kept fixed, that is 1000 with peak to peak. So you will be having a waveform from +1 to -1. We have kept the carrier frequency as 1 kilohertz. Now this is the reference waveform. This should be 1. Then the frequency, okay, I'll make it as 0.8 because you can vary the amplitude of the reference signal from 0 to 1. So this is again 0.8 for symmetrical pulses. This is very important. Frequency has to be changed. Okay, then again, this is what you can say 0.8, and this one is of 50. Okay, so in this way you can, I think this is now done. This part is done. Now, what is important that you need to give the pulses. Fine. So, how to give the pulses and where to give the pulses? So, for that, you need to have the on-off controller. I think both the switches are operated in a complementary fashion. When this switch is on, this should be kept off. Otherwise, what will happen if you apply the simultaneous pulses to both these switches, then there will be a dead short circuit. Okay, so considering that concept, we will have to go for the NOT gate. I think NOT gate is available, right? So I think NOT gate is available. Okay, so this is so we will write give NOT signals, right? Okay, so this has been done. So now the on-off switch controller. This very much required. This is very much required. We will be placing this right. Very essential because there is the difference between the control circuit and the power circuit. You need to isolate the control and the power circuit. You cannot directly connect the control circuit and the power circuit. What will happen? The current will flow from the power to control and control will get damaged. So to provide the protection, this has to be done. Okay, so now I think the work has been finished. I just have to connect the wire. That's why actually I have taken the entire interface for drawing this because for the clear understanding. Now, okay, so again this has to be made connected. Okay, give the pulses has been given here. Okay, the NOT gate is there. You can see the symbol, the symbol is there. Okay, now, right, this is the symbol. Okay, the connection. This is about the third switch which we are operating. Right. Okay, this has been done. Okay, the waveform, right, the complete thing has been done. So now we'll try to obtain we'll try to do the waveform. So for that, the voltage probe is required. Yeah, voltage probe is required for this, this, okay. So now maybe the connection, I don't know whether the connection has will be proper or not, but still, yeah, it is between these three. Okay, I can make the, yeah, I will place this here only. So for a clear understanding, because we will have to replace the load by RL load. This load should be balanced one. This should not be unbalanced because otherwise there will be a power quality problem which you might face. Okay, so now let me check what the load we have set. I don't know about the, yeah, it is 10 ohms only. Make some, right, that is VA, VA display, click on the display. If you want to display the things, then again, this is VB. Okay, right, very much right. Then this is the VC. Okay, right. So now everything has been named. Okay, so whether let me check. Okay, now the simulation control is required because without this, nothing is going to be achieved. Okay, so now whether let me check it again whether I have placed it right or not. Okay, 0.8. Right. The one thing which we have left is about the phase angle because there are three phases. So 120 degree, you will have to put this is the 240 degree. It is very much required because we are having three phases and there will be a phase shift of 120 degree between the three, you can say, gating pulses also. Gating pulses also, right? So now I think the everything has been made. We'll wait for the waveform. So the VA added. Okay, right. I think we have got the thing. This is very much looking like a sine waveform. And if you can just calculate the THD of this waveform, it will be very, very less. And if you just connect a filter after this, so the entire harmonics will be eliminated. Similarly, you can go for the other two phases. I think this one is more than sufficient. Okay, right. It is also right now. Okay, very good. The thing has been, yeah, right. It's wonderful. Now, we will make some connection. Now, I think the experiment has been done. This is more than sufficient. But what we can do that we can just connect the RL type of load and we'll try to see whether the waveform will be sustained or not, or will there be any changes will be there or not. That we can check it out. Okay. So again, we'll make the connection. I don't know what is the value which we have taken. Let it be, um, it should be 100 millihenry because in the last experiment, uh, we have taken the value as 100 millihenry. So we'll do that. Okay. So this is 100 E minus 3. You can write in this fashion also. Uh, yeah, this is acceptable. This is acceptable in the MATLAB also. You can do that thing. E minus 3 and this one is 100 millihenry. We will check it out whether the things are in the proper fashion or not. Okay, I don't know whether what type of voltage because I just want to check. I don't know whether, yeah, this is coming. So something, right? Again, this is okay. No, we'll check the current now. So for that, you will just have to just a minute. We'll check the current. So current probe is connected. Okay. Now we need a wire tool for that. So that should be the thing. Okay. Now this is okay. Okay. Again, we'll run the simulation. Let it just want to check the I2 current. Yeah, it is coming to a where it is nearly a sine waveform. It is nearly a sine waveform. If you connect a filter, the harmonics will be eliminated. So I think we are successful in bringing down the harmonics from the square wave inverter to a SPWM inverter. This is all from my side. Any doubt you can always ask me. Thanks a lot for watching.